Well, hello and welcome to the series of videos on essentially analytic number theory. We're going to have a little journey through analytic number theory. I'm going to begin with just a very brief introduction, and then we'll have a look for a few videos at some classical number theory before we start the analytic number theory. So these notes are probably designed for someone who has done a first course in number theory, because I will be skipping over lots of bits and pieces, and also you will need to have a reasonable amount of basic analysis and some complex analysis in order to perhaps follow all of the bits and pieces that we're going to be looking at. So number theory is essentially concerned with the properties of natural numbers and the integers, the natural numbers being the numbers 0, 1, 2, 3 and so on, and then the integers including all the negatives. The ancient Greeks studied some basic properties of numbers, not negative numbers of course, and Euclid described some of these results in Book 10 of the Elements. Diophantus, around about 250 AD, he studied certain types of equations where we're looking for integer solutions or rational solutions, and these are called Diophantine equations in his honour, which may or may not have integer or rational solutions. Diophantus' work of course inspired the work of Pierre Fermat from 1601-1665, who's often regarded as the founder of modern number theory. He tried to develop number theory in some sense as a systematic branch of learning, although he basically concentrated on solving particular problems. Major strides forward were taken by Euler and of course later on by Gauss. Nowadays number theory is divided into a range of categories, including algebraic number theory, analytic number theory, which is what we're ultimately going to be getting to, probabilistic number theory, geometric number theory, and so on. So these notes will deal with the rudiments of classical and analytic number theory. So I'm going to begin with some classical number theory, and again I'm assuming that those who are interested in this have already done perhaps a first course in number theory, so this should be not completely new to you. So we take a positive integer n, and I'm going to use the notation z sub n to denote the ring of integers modulo n. Now by a ring of course we mean a set, vaguely speaking, where we can add, subtract and multiply but not necessarily divide. We have the integers mod n form a ring with a 1. There's also a 0 object and various other axioms hold, but all of the basic things you'd want to be true are true. So the associative law, commutative law, and so on. So in the case when n is prime, when n is a prime p, z sub p forms a field, which means that you can do division. So every non-zero element has a multiplicative inverse. The invertible elements in the ring z sub n are those that are co-prime to n. So for example, if you've got z6, then the elements in z6 which are invertible are only of course 1 and 5, because 2, 3 and 4 are not co-prime to 6. So these numbers are going to be called units in the ring, and we're going to denote these by u sub n. So U12, for example, consists of the set 1, 5, 7, 11. These numbers are all relatively prime to 12. And of course, if p is a prime, then u sub p is just all of zp, then take away 0, which obviously doesn't have an inverse. Instead of writing GCD of a and b, I'm just going to write brackets ab for the GCD. And you'll recall that very fundamental result, sometimes known as Bezout's lemma, that if you've got d as the GCD of two integers a and b, then you can write d as an integer linear combination of the two numbers you started with. That is, you can write d as ax plus by for some integers x and y. And in some sense this fundamental fact is it is a fact which is very fundamental in number theory. and very important, the so-called Bezout's lemma. A couple of basic theorems, which I won't go through the proofs of. This you would have covered in an earlier course in number theory. So if n is a positive integer and a and b are integers, the linear congruence ax is b mod n has solutions if and only if you need the GCD of a and n, the biggest common factor of a and n, has to divide b. And in the case when it does, then there will be d mutually incongruent solutions modulo n. Famous result, the Chinese remainder theorem, deals with simultaneous linear congruences, and it says if you've got a sequence of congruences, x is congruent to a1 mod n1, a2 mod n2, and so on down to ak mod nk, then provided all of these moduli, if they are pairwise coprime, that is, if you pick any pair of these and they have no common factor, if they're pairwise coprime, then this system has a unique solution. X is congruent to n. It has a unique solution, I should say, modulo n, where n is the product of all of these. So there is some unique value x which satisfies all of these congruences modulo capital N, which is the product of all of these. Now I'm going to do an example of one of these. So this result is very useful also when dealing with a congruence equation of the form fx is 0 mod n, since we can uniquely factor n into the product of prime powers and consider the congruence with respect to each prime power, and if you can solve those separately, you can then recombine them to obtain solutions if they exist. Just as a simple example, I'm going to just quickly solve this system here. X is congruent to 1 mod 3, 2 mod 4, 3 mod 5. And here is the solution to this. So I'm going to do this in a probably slightly novel way. There are many ways of solving this system of equations. I just note that 3, 4 and 5 are pairwise relatively prime, and so I know this has a unique solution modulo the product of all of these, which is 60. And I'm going to actually write down the solution but with a couple of parameters. And the way I construct these is as follows. You take the first number, which is 1, and so I claim my solution is x is congruent to 1, that's that one there, plus 3 times something, that 3 is coming from there, plus 12 times something, and the 12 is coming from the product of these two, and the answer then is given modulo 60. If I had 4 congruences, if I had, say, x is congruent to 4 modulo 7, then I would have had exactly this, except I would have also multiplied this by this plus this and added on a 60 gamma, and the answer would be unique modulo 420. So this is a sort of novel, clever way of solving these congruences fairly quickly. Equation 1 is automatically satisfied, because if I read this modulo 3, then that disappears, and x is congruent to 1 mod 3. I plug it into equation 2, and the way I've constructed this is that when I read this modulo 4, that term disappears. And so when I read it modulo 4, I just plug it straight into equation 2. I get 1 plus 3 alpha is congruent to 2 mod 4. And I can solve that pretty quickly. This says 3 alpha is congruent to 1. If I multiply, say, both sides by 3, then I get 9 alpha, but 9 is 1 mod 4, so I get alpha's 3. If you will, this is alpha is 3 mod 4, but I'm going to be plugging alpha back in a moment, so I may as well just take alpha to be 3 itself. Finally, I now know what alpha is, so alpha's 3, so that means this is 10 plus 12 beta, and I can plug this one back now into equation 3, and so I'm going to get 1 plus 9 is 10, plus 12 alpha is congruent to 3 mod 5. So 10 plus 12 beta, I should say, is congruent to 3 mod 5. And again, I can solve this pretty easily. Mod 5, that's 0. I can double both sides here. And I get beta is 4. And then I can simply plug that back in. Let me check this is correct here. Yeah, so this you get beta is 4. So what did I do here? Modulo 5, that's 0. Modulo 5, this is 2. And so I can multiply both sides by 3. 3 3s are 9, which is 4 mod 5. So you can find out what beta is. Finally, you can plug that one back up into the original solution here. So alpha's 3, beta's 4. Plug that through, you get x is congruent to 58 mod 60, and we can check that this is indeed, this is congruent to 1 mod 3, it's 1 plus 57. It's 2 mod 4, it's 2 plus 56, which is divisible by 4. And it's 3 mod 5, because this is 3 plus 55, which is 55 is 0 mod 5. Okay, so that's just a little example there of solving, doing a Chinese remainder theorem. Well, of course, the next main result one comes to in classical number theory is Fermat's little theorem, which is very, very useful, discovered by Fermat, not written in this form. The congruence notation was, I think, introduced by Gauss. And so Fermat wouldn't have stated it quite this way. He would have said a to the p minus 1 is divisible by p. Anyway, the Fermat's little theorem states that if p is a prime number and p is not a factor of a, then a to the p minus 1 is 1 mod p. Lots of examples of this. Lots of proofs, I should say, for this. You can find them in most number theory books. There are lots of different simple proofs of this. The simplest one I find is to take the numbers 1 up to p minus 1, multiply them by a, and then compare and do some calculations, and you find this falls out. I'll leave you to have a look at some number theory books on this one. So to generalize this, and this was the interesting bit, of course, Fermat knew this worked for primes p, but didn't quite see what happened if p is not prime. It was Euler who realized how to generalize this, which is not trivial, in fact. It is once you know the mathematics, but at the time it was quite a clever thing to do. And to do this, we need Euler's phi function. And we'll say a lot more about Euler's phi function later when we start looking at the analytics of this. So this is just equal to the size of this set. So you take all the numbers that are less, all the positive integers that are less than n, and you count the number which have a GCD of 1. That is, so for example, phi of 12 is 4, because as we saw before, the numbers that are relatively prime to 12 are 1, 5, 7 and 11. There's 4 of those, and so phi of 12 is 4. If p is a prime, then phi of p to the alpha, well, this is easy to prove, because if you just start listing the numbers from 1 up to p to the alpha, and you take away the ones that are not relatively prime to p to the alpha, well, the ones that are not relatively prime will be p, 2p, 3p, up to p to the alpha minus 1 times p. And so the number of numbers that are relatively prime to p to the alpha is all of them minus that many multiples of p. Now, the difficult bit to prove, which I'm not going to prove again, you can look up number theory textbooks on this one, is that if you've got two numbers that are relatively prime, then beautifully this thing splits. Phi of mn is equal to phi of m times phi of n. That is, given the way we've defined Euler's phi function, this is rather remarkable that this should happen, and we'll give a name to this later. This tells us that phi is a multiplicative function. Phi is multiplicative. Now, these two formulae here enable us then to find phi of n for any positive integer, as I'll show in the next example. So these two formulae are really quite key. This is not that easy to prove. It takes a little bit of work. So to, just as an example, I'm going to find phi of 7878, just as an example of how we use this. So what you do is you take this number and you can uniquely factorise it into prime powers by the fundamental theorem of arithmetic. You can uniquely factorise this. Well, it's 78 times 101, and 78 factors into 2 be 3 be 13. So you can uniquely factor this. Now you can split this because phi is multiplicative, so it's 5, 2, 5, 3, 5, 13, 5, 101. Now these are all primes, so phi of any prime p is just p minus 1, so it's 2 minus 1, 3 minus 1, 13 minus 1, 100 minus 1, and we get 2,400. So there are 2,400 numbers between 1 and 7,878 that have no common factor with this number. And that's Euler's phi function, which I hope you met in an earlier course in number theory. Okay, having that then, we now can come back to Euler's theorem. Euler's theorem now tells us, now states that if we have two numbers that are relatively prime, and m is a positive integer, then a to the phi of m is congruent to 1 mod m. So remember in Fermat's little theorem it was a to the p minus 1 if p was prime, and the p minus 1 now gets replaced with phi of m when we want to generalise this to a non-prime modulus. Now this U group, another way of defining phi of m is to say that phi of n is the number of elements in un, because un consists of the elements that are invertible mod n, and they're of course just the numbers that are relatively prime to n. Now this forms a group. Now in this group you can multiply two objects in un and they stay in the set. There's obviously an identity and the associative rule holds, and every element in here by definition has an inverse. So the obvious question, if you've done a little bit of group theory, is to say when is this group cyclic, and the answer is it's cyclic if and only if you get a little bit of noise at the beginning. 1, 2 and 4 are sort of funny special cases, not very interesting, but this is cyclic if and only if n is a power of a prime, an odd prime I should say here, not 2, or twice the power of an odd prime. So that's again a fundamental result from number theory, that this group of units, this group of invertible elements, this group of numbers that are relatively prime to n, forms a cyclic group, that is, it has a generator, if and only if n is one of these numbers of this shape. In this case, there are in fact then 5 phi of n generators. And so, of course, in the case when n is prime, phi of p is p minus 1. So in the special case when n is a prime, there are 5 p minus 1 generators. And these generators are called primitive roots or primitive elements. And these again are quite fundamental in number theory. So in the case where p is prime, we have phi of p minus 1 primitive roots. A number a is said to have order k mod n. Simply means that k is the smallest positive integer, so that when I raise a to that power I get 1 mod n. Thus if a is a primitive root, so a is a primitive root, then if and only if a has order 5n. So a is a primitive root if and only if it's got order 5n. In the case of a prime, so a is a primitive root mod p if and only if it's got order p minus 1. So I'm just summarising basic results here from classical number theory that again you can find in most books on the subject. Wilsons Theorem is an interesting little fact. It's one of the very few theorems in number theory that has p is prime if and only if something. So in some sense this characterises a prime and also tells us how to check when a number's a prime. You just have to check this thing. So it says P is prime if and only if P minus 1 factorial is minus 1 modulo P. By the way, it probably has nothing to do with Wilson. This probably goes, in fact, back to Fermat, but Euler, for some reason, called it Wilsons Theorem, and the name is stuck. You might think at first glance that this is a nice way of checking when a number is prime, but of course computationally this is not a good way of checking when a number is prime, because P minus 1 factorial becomes very massive even for relatively small primes, and so it's not a good way to check whether a number is prime or not. But it is an equivalence for P being prime. Now, an immediate corollary, and this is not very difficult to prove either. You've seen in elementary number theory books, you just write down the numbers 1 up to P minus 1, and you look at this, you see that every one of the numbers in that list cancels with one of the other numbers. You need to check that the numbers from 1 up to P minus 1, each of them has an inverse different from itself, and so when they cancel out, all the terms cancel except 1 at the beginning and P minus 1 at the end, and P minus 1 is minus 1 mod P. You can check that from any sensible book on number theory. Interesting corollary to this is that we can solve x squared is congruent to minus 1 in the case where P is congruent to 1 modulo 4. So let me read that again carefully. Suppose P is a prime congruent to 1 mod 4. So a prime like 5 or 11 and so on. Then you can find the square root of minus 1 in ZP. That is, x squared is congruent to minus 1 has a solution modulo P. This is the first instance where one sees the primes splitting into two classes, the 1 mod 4s and the 3 mod 4s. You'll see many examples of where this happens. The 1 mod 4s and the 3 mod 4s. So you can find the square root of minus 1 modulo P in the case where P is 1 mod 4. Now, my little proof of this, which I'll take you through, it's worth seeing here. So this is the corollary to Wilsons Theorem. So we take P as 1 mod 4, and that means that P is 1 plus 4 times something. So P minus 1 over 2 has to be an even number. So it's got to be 2k for some integer k. Now I'll write down Wilson's theorem, which says P minus 1 is congruent to minus 1 mod P. And P minus 1 factorial simply means 1, be 2, be so on, up to P minus 1. And what I'm going to do is I'm going to rewrite this list here, or this product. I'm going to stop halfway, that's P minus 1 over 2. I'm going to write the last few. This is P minus 1, P minus 2, P minus 3. And if you look at the try and pattern match here, it suggests that the last one, this next one here, should be P minus 1 over 2, which I leave you to check is correct. That gives you P plus 1 over 2. Now, if you read this modulo P, then looking at from this end, and by the way, this is all still congruent to minus 1 mod P by Wilson. Now, if we start looking at the brackets this way, P minus 1 modulo P is just minus 1. P minus 2 modulo P is minus 2, and so on, all the way up to minus this one, which of course are all of these numbers again, but with a whole string of minus signs. So if I read this way modulo P, I'm just going to get these numbers modulo P, so I get that squared. And I'm going to get a whole pile of minus 1s. In fact, I'll get P minus 1 over 2 minus 1s in that product. And again, that's still congruent to minus 1 mod P. Now, I can then simply, this mess here is just P minus 1 over 2 factorial all squared. Now, we said before that P minus 1 over 2 was 2k. We saw back up here, if P is 1 mod 4, then P minus 1 over 2 is even. So if you raise minus 1 to an even power, you just get 1. So that disappears, and that's because P is a 1 mod 4 prime. And behold, I have given you now the solution to x squared is congruent to minus 1 mod p. I have found explicitly a solution. The solution is x is p minus 1 over 2 factorial. Because when you square this beast, you get minus 1 mod p. And so there is a nice little proof that you can take the square root of minus 1 if p is a 1 mod 4 prime. And I'll leave you to check that if p is a 3 mod 4 prime, then this doesn't work. If p is a 3 mod 4 prime, you can show that you get a contradiction there. So this brings us to, we've had our corollary. So we just note that the converse is also true, i.e. if p is an odd prime, then that has solution only if p is 1 mod 4. This in fact follows from the following theorem we're about to state, theorem 1.1, and we'll state this fairly important theorem again without proof. I'll leave you. This is a tricky little theorem, but it's a very important one, and it's one you should either attempt to give a proof of yourself or have a look up in a book. So n is, if n is an integer for which un admits primitive roots, okay, and we've seen before what n this works for, and suppose that a and n are relatively prime, then the congruence x to the k is congruent to alpha mod n. So now we're trying to solve x to the k is a, so we're generalizing this x squared is congruent to minus 1 quite a bit. This has solutions if and only if a to the 5n over d is 1 mod n, where this d is the GCD of k and 5n. Furthermore, if it has solutions, then it has exactly d solutions. And so this is a lovely, quite general result, and I suggest you have a look at this one up in some books on number theory and have a look through the proof. As a special case of this, also originally due to Euler, if p is a prime and a and p are relatively prime, then the congruence x to the k is congruent to a modulo p, has solutions if and only if a to the p minus 1, because now 5p is p minus 1 over d is 1, modulo p, where d is the GCD of these two. So that is a very nice result. This was result by Euler, and this is a nice generalization of it. In the next section, we'll start having a look at quadratic residues, and we'll get to the Gauss's famous quadratic reciprocity theorem.